In this screencast, we'll talk about analysis of variance, a new hypothesis test. And we don't have confidence intervals anymore. But analysis of variance, well, last week we talked about whether two population means were equal. A null hypothesis looked like that the mean of the first population was equal to the mean of the second, and the alternative might look like mean of the first is not equal to the mean of the second, or greater than or less than. And we used what was called a t-test for two population means with our procedure template. With analysis of variance, we ask whether multiple population means are all the same. So you can imagine doing agricultural research and wanting to know whether no fertilizer, 20 pounds an acre, 50 pounds an acre, 100 pounds an acre had different yields of corn in bushels per acre. Or you might ask whether math majors, English majors, psychology majors, nursing majors, and art therapy majors all had the same mean average starting salaries when they graduated college. In our example, we're going to ask this question. Do people in excellent, very good, good, fair, and poor health all have the same average age? We kind of guess that they don't, but this is where we do statistics. So before we do anything fancy, let's just look at the box plots for the 5 groups. So this is from our health data, and remember these numbers here are the medians, not the means, but still it certainly looks like that the people in excellent health are relatively young and the people in poor health are a fair amount older. On the other hand, there's a lot of overlap in the group. There are plenty of older people in excellent health up to here and all the way up to here, up to age 80. And people in poor health that are relatively young. So these 5 groups have overlap, and we can't just look at this and say, oh, they don't all have the same mean age. So this is what Anova does for us. After all, this was a sample of only 1,000 people, and maybe it's just by random chance the numbers came this far apart from each other. So you use Anova when you have I different populations for some number, so 10 different populations, 3 different populations, anything more than 2. And the null hypothesis is that the mean of the first is equal to the mean of the second is equal to the mean of the third, that all the means are equal. And the alternative is just they're not equal. It could be that 4 of them are the same and the 5th one is different. It could be that no 2 of them are the same. It could mean that 2 of them are the same as each other and the other 3 are the same as each other, but they're not all 5 the same. Anything except that they're all not equal, or anything except them all being equal, that means the alternative hypothesis. So the null, they are all the same, however many populations you have, and the alternative is that population means are not all the same. So the basic idea is you look at how different the sample means are from each other, and you compare that to the standard deviations within the samples. So the difference between the different populations and the differences within the different populations. And that's really what our t-test did for 2 populations too. So we compute what's called an F statistic, not a Z and not a T and not a chi-square, which we'll talk about later. We compare the differences between the populations to the difference within the populations. That's what's going on. Of course, Excel is going to do all the hard work for us. We create what's called an F statistic, and it's a different F statistic depending on the sample sizes and how many groups you have. So that's the degrees of, so-called degrees of freedom. But we're not going to worry about those technical details because Excel is going to do all that for us. We just use Excel to get a p-value. We're just asking the question, gee, could all these groups have the same mean, or is there really evidence that they don't all have the same mean? So there's some assumptions that we have independent simple random samples from each population, 1 from each population, and each population has a normal distribution with unknown mean. Now, you can't really know that it has a normal distribution. If the sample size is large, that's not a problem. If it's small, you maybe have to worry about that and check that it's not really skewed. It also assumes that all the populations have the same standard deviation. Well, that's quite a big assumption. Again, if the sample sizes are large, not such a big deal. And in practice, you can use Anova if the largest sample standard deviation is no more than twice the smallest standard deviation. In this course, we're not going to worry too much about the assumptions that you need to do all of our statistical procedures, but you should know that there are assumptions and that there are things that really ought to be satisfied before you do a statistical procedure. Just because you have numbers doesn't necessarily mean you can do one of our tests. Okay, so how do we do this in Excel? Well, in the Data tab, we choose Data Analysis, we choose Single Factor Anova, tell it where the data is, and we'll get a printout. We'll get an output that looks like this in this case. So there's a whole lot here. Let's just see what the easy ones tell us, what some of them tell us. The people who are in excellent health, there were 241 of them, and their average age was 41, almost 42 years. People in poor health, there were only 30 of them, their average age was 59. Well, those numbers are quite different. These averages are different from each other. But of course, the whole point is that difference statistically significant? Maybe this could have happened by random chance. And then down here, we get the p-value. This is Excel's way of saying that it's a really small number. This is Excel's way of giving a scientific notation, 1.72 times 10 to the negative 11th. So that's a decimal point, 10 zeros, and then a 1/7. Tiny, 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 practically zero. And of course, what that tells us is that if these populations all have the same average, then it would be almost impossible to get sample means that were this far apart. Almost impossible. 1 in 10 billion, or maybe it's 100 billion. 1 in about 170 billion. Very, very tiny chance. So that tells us that we're going to reject the null hypothesis and conclude that the populations do not all have the same mean. That people in excellent health, very good, good, fair, and poor health do not all have the same average age. So that's how Anova is done. In the PowerPoint for this screencast, I've got a couple more examples, questions. So this one is, do students in all 4 business concentrations have the same mean GPA, much smaller sample sizes? And this is from some university. And another example, does planting different number of corn plants per acre lead to different yield in bushels per acre? And I'm just leaving these in the PowerPoint so that if you open the PowerPoint, you can grab this data and do these as practice.